going to record this session, so it doesn't have a video for you or anything, so it'll just be your voice in the background. So don't be afraid to ask any questions. But there's not going to be any. There won't be any kind of. I may post it some year later on down the road, but if I do, I'll always kind of go back and ask anybody that participated if they had object to that. But anyway, the review for tonight was two things for sure that I wanted to try to get out of the way, and one was Ohm's law, kind of all the basics, and cover those, and as far as the mechanics of the way I do my Ohm's law stuff. But the second thing was a voltage drop, and kind of get that out of the way, and they both kind of follow the same format. And what I like about it is, let me see if I can find that sheet that I just passed a second ago. You're familiar with this. You're familiar with this Ohm's law wheel right here, I guess, or
I actually got one of those right on the front of my code book.
Okay.
Too. Okay.
All right. And they give you one. They give you one. By the way, while you're in the test center, so you'll get one while you're in there. That.
Oh yeah, it was on the book. Okay.
Yeah, let's see. Insert a blank page. And then I'm going to do page layout. I'd like to do it on orientation landscape. And let me get this set up real quick. All right. Now that give me a blank page. There we go. All right. So I've got, see if I can take this one right here. I've always looked at the Ohm's law stuff in a more simplified manner. I wouldn't say always. I'd say in the last, 5 or 6 years. And but previous to this, I've always used the PIE and the EIR for the two basic formulas. And most guys, pi and EIR being the resistance formula for electromotive force, and I for intensity of current, and R for resistance values. But the truth be told, nobody uses E for voltage and I for intensity current. I mean, it's just not something that you use very much.
Yeah.
And so if you'll
go back and relearn it.
Yeah, I tell you. Yeah, I don't know why it's still, we just kind of, I guess that as an instructor, that's what I taught, because that's what I learned was the EIR and the PIE. And then I watched this YouTube video once, believe it or not, and it was a guy that taught electrical classes, and his stance was, look, nobody has referred to this stuff this way in 100 years, and so your guys that are learning this stuff aren't going to be thinking about it, and they have to convert an E every time they see it, and then they have to convert an I every time they see it. And so if you'll just make the change and switch over to this VAR and the WAV, it's a cognitive thing that makes it instantly an easier, more recognizable format. And I was resistant to it, because trust me, I don't like to change anything, especially if the recipe is working all right. Don't fool with it. But the bottom line is that I tried it a couple of weeks in some of my classes, and the ability of guys to be able to just kind of instantly see, or almost intuitively feel the relationship between the different parts and pieces was quick, and it was pretty impressive how easy it was for the guys. So I made the conversion, and I've never looked back since. And so if you feel like it's kind of hard to look at it as a WV and a VAR, just give it about a day or so, and the next thing you know, you'll never go back either. But at any rate, the two main formulas that they use on this test that solve, I've not seen a single PSI exam question on any state that I've taken, or any state that I'm aware of, that I couldn't answer or solve with these two formulas, the WV and the VAR. Which means that the bottom line is that little circle's nice. You got all those these other parts of the pie, and if you wanted to learn this whole circle, it'd take us about a week, and we'd have to. I mean, there's plenty of stuff to kind of review just in the format of what operation do you do first, and kind of what order they have to fall into. But this is a nice, clean, easy way to look at it. And and the relationship is really easy to see. This is a mathematical relationship, is what this circle represents. So this line that separates the bottom half from the top half is a division line, and then the line in the bottom down here is a multiplication line. And I
was trying to teach myself left to right was times, and then up and down was division.
I'm with you. This is easy. this is easy and it's instinctive. And like I said, once you get used to it, it'll be you'll find that almost every formula that I've ever seen in the electrical trade, you can use the same kind of format with, and it's really kind of nice because after you get down to it, like all your transformer equations, your IP over IS and all your your transformer winding formulas and stuff, those will fit into one of these formulas. So will our voltage drop, which is the thing I really like about both of them, is I can knock out the voltage drop and this at the same time, and it won't even hurt. I promise. You'll be after about a week, you'll never have to worry about memorizing a formula again, because this WAV, this VAR, if you can just remember this relationship part with this line here being the division, and of course the bottom line being the multiplication. I always have to know two values to serve for the third value. So I need to know which two. So if I'm looking for the current or the amps in this case, I'm just basically dealing with the W and the V left over, and I'm going to do the operation that this circle represents by taking the voltage and dividing it into the watts or the volt amps or the power or whatever value that they give me in there for the W. And of course the W and the P and the VA are all interchangeable. So you could look at this as a W or a VA if you're dealing with. Yeah, that's right. And just a quick note, all your watts and volt amps and power, true power and apparent power, it's 100% unity. So there's not any power factor losses or efficiency losses. So it's you can interchange a watt and a VA just fine without any worrying about there being any kind of losses there. All right. So that's that part. Let me make this a little bit bigger so that'd be easier to see. And move down there. All right. Resistance.
Test, it seemed like there was a lot of voltage drop questions on there.
Yeah. Was it voltage drop as it relates to like resistors?
You know what? I'm trying to go back, and I think it was just voltage drop questions, and I don't think there was any. Would there be percentages in there? I don't.
Yeah. There would be. That's right.
There might have been one of that. But man, it was, and I knew to study that up for missing it from the first time.
Yeah.
She didn't even let me take my code book the first time, but this second gal did on the theory. But yeah, I should have brushed up again on the I thought I had the voltage drop down.
I tell you, here's the thing. This is the main formula right here. Can you see that little yellow circle now?
Yep.
All right.
Let me constant amps and drop or lanes.
Well, I always you were a fan of the '90s band. Back in the '90s, there was this kid band.
Yeah.
It's called Two Kids on the Block.
Yep. Yep.
You remember that band?
Yeah. Oh yeah.
It's actually I think it's New Kids on the Block, but
I think it is.
Yeah, but
that's right. I remember Kids on the Block.
I would never admit that to anybody if I were you.
I know. That's right.
Let me see one second.
That's right.
Let me crop this thing real quick. I'm trying to make this let's see here. I'm trying to crop it and it's not letting me do that. How in the world do you crop something?
Oh man.
I tell you, Windows, I swear to goodness, you could be I spend more time dealing with my computer, it seems like, lately than I do anything else. Anyway, you can see it fairly well enough. I don't have to do too much else with it. So, but you'll notice that it's the same circle format that the VAR and the WVR, which means that it's the same kind of relationship. And for me, if you take the time to kind of learn this part up here, then this naturally kind of falls into place with it. And you're always going to solve for one of the bottom variables, which means this particular formula, the two kids over the VD and the circular mills like this, that represents either the voltage drop formula or the circular mills formula, which is the wire size, as far as that goes. So it takes the place of those two. And then the other one, which I'm going to bring a copy of down here real quick, is this black circle that is the exact same formula. It's just mirror image of it. So this is something that after a couple of times, it's kind of an easy thing to remember. It's two kids on the block, and then if you're solving for either one of the other variables, it's just a mirror image of the other pair. Now you always have to solve for one of the bottom variables, which means that if I'm solving for wire size or if I'm solving for voltage drop, I'd use the top yellow circle because that's where the two bottom values are. And if I'm sizing for a maximum distance, which is what the D stands for, if I'm sizing for the maximum current, which is what the I stands for, I'm gonna have to use this formula down here because it's a bottom value down here.
Yeah, and I found that kind of being confusing to tell what they were asking for in the question. Was it voltage drop or how many amps drop? It was kind of confusing.
Yeah.
You know? Man.
Well, there's only so much that they can do. I mean, ultimately, after you get through all of the the intricacies of a question, a test question, there's only ultimately one way to ask you to solve for something, and that's to sometimes it may take you a little bit of work to get there. You kind of have to work your way through the wording of the question, but ultimately, if you ask yourself, what exactly is the ultimate outcome here, sometimes it's easier to kind of force your brain to look at it in a little different manner. Now you're under a gun, and it's kind of if you don't feel confident with those types of formulas, then it kind of seems like it'll wreak a little havoc and be kind of hard. But there's only 4 things they can ask you for in a voltage drop, and that's going to be either the percentage of the system voltage that you're allowed to lose, or the wire size, the maximum length of the circuit, or the current. And so if you find yourself struggling with trying to find what they're asking you for, make a list of all the known values that they give you in the test question, because you have to have everything except for the one value that you're looking for on any of these formulas. And
they'll probably give you 2, right?
Well, they may give you too much, or they might be, like, for example, let me see. Let me just type it up here. Might be a little easier. There's a question that they were asking for a while on a journeyman's test here in Texas, that they gave you a motor, and the motor was a 2 horsepower single phase motor that was at, I think, 13.2 or 13.3 FLC value. In other words, when it was running under its normal speed after startup and then kind of settled down to just to run on its normal demand load on the conductors, it was running about 13.2 amps. So it's 13.2 amps. Let me put that A in there so we remember what that is. And they were asking for the maximum distance here. And let's see, what else did they give you? It was on a number 12 wire on a branch circuit with number 12 AUG. And they wanted to know what the maximum distance for that circuit was.
Yeah, wow.
Let's see here. What?
It seems like they had like the constant or in parentheses. They said use this for something in parentheses. Whatever the constant of copper.
Yeah. What is the maximum length of conductor for this install? All right, so let me get these circles out of here because I kind of got a little too much there. What that kind of went a little too far on me there. Just trying to have a whole blank page here for all this, and I just end up accidentally deleting something that just brought it all back up. All right, so we've got basically just, and I'm not going to start and get into detail with it here, but just to kind of give you an example. That's going to use one of these 2 formulas up here when we're talking about voltage drop. Now, you can have a voltage drop occur, or a voltage drop question, with a resistor or a set of resistors in series. And so that's a different voltage drop. In fact, it's really a voltage loss kind of question versus a percentage voltage drop up here. Because once we have conductors in parallel, we shouldn't have any voltage drop technically or theoretically, or wouldn't want one to occur if we could help it.
Yeah,
so
right. Voltage should be the same, right?
That's right. So it should be at the same at the starting point, at the end point, and all points in between. So, when you start to occur a distance and a small conductor for the load that it's carrying, then you do get a little bit of voltage drop over the conductor, and that's line loss or whatever, that branch circuit loss, or could even be a feeder loss if you have a severe enough load on too small of a feeder. Either one of those, that's what these 2 formulas up here deal with. And so when you're looking at this question up here, the 2 horsepower single phase motor and the FLC value and branch circuit, and we're looking at a question that's asking you for a branch circuit effectively, because they're telling you that you've got a branch circuit here with number 12 wire. And why that's important to you is this up here. Let me pull up this other table. This little table is something that it's not a big table, so I would probably just kind of pencil it into your book. And since you don't have voltage drop, you don't really have any Ohm's law or voltage drop anywhere in your code book, it's probably easier to just pencil this on. Like if you look in your code book back on page 853, I believe, and 855 are 2 pages. Look in your code book real quick and see if there's anything written on page 850. Try 853 and see if that works. Let's see, size and position. I'm going to do text wrapping is what I'm looking for in front of text.
4. Okay, 853. There's a blank spot.
Yeah, and then 855 is the same way. And those are 2 phenomenal places. They're not all the way at the end of the book, so they're not necessarily on anybody's radar. And so they have to be kind of. Yeah, and so I would reserve those pages. There's about 7 pages throughout the back of the code book, some in the front that kind of give you some good spots like that. I would try to reserve those and use like half of it for Ohm's law and half of it for voltage drop, and then use the next page for maybe your junction box size or anything else that you want to do that may be a code specific section in your code book, but there's nowhere to write good notes on that area of the code book. If that makes sense.
Probably tell us how to write in there during the class.
Oh yeah, you'll get quite a bit of that. So
I'll wait till then and put all that in. All right.
See here, I'm going to paste this as a picture. That's what I meant to do earlier, and that would have been better for me. See if that works.
The first gal, boy, she was on it like a hawk, but then I went, and that's because I had taken it on a Saturday, and then when I went, it was a Monday, and there was a totally different gal. But
so
the first one,
the Saturday lady was harder. The Saturday lady.
Yeah, she was more strict. Yeah.
It's usually the other way around, but
that's what I was thinking. Yeah. And she's the one that wouldn't let me use my code book for the theory, where the lady on the Monday that wasn't so strict, she let me use my code book.
Wow. Now, see, that's usually, like I said, it's usually the other way around. It's usually the Saturday people that are really relaxed, and the Monday people that just don't care as much, or the Monday people that just got through their meeting and they're ready to get those lying, cheating suckers, kind of thing.
That's right. When I took my journeyman, I swear I could kind of figure. I think I missed each one twice, but then I passed. But I could kind of figure out the test. But boy, this master is pretty tough.
Yeah. Do you remember any of the voltage drop questions you had, or any of the specifics to any of it?
They were kind of just like what you had asked there when you were writing that one out, but then they had the constant. It says use this in constant in parentheses for copper, or aluminum.
Yeah,
the 12 something for copper.
The 12.9. I'll tell you what, I just got this all messed up. There's 2 numbers that go with these circles, and if you look on chapter 9, table 8, it's on page 767, I believe, of the code book.
Okay, let's see. I'm going back to that page 767. Yep, there it is. Table 9, chapter 9. Okay, got the circular mills, the size of the wire, the ohm KFT, uncoated copper.
Look at the ohms per 1,000 feet of uncoated copper at 1,000 circular mills. So almost at the bottom of the page there. And the only reason why this works out is because it's 1,000 ohms per feet under the uncoated copper there, and it's the uncoated copper, I believe, and it's 1,000 circular mills. Yeah, 0.129, right? If you were to just move that decimal place over a couple of spots, and that you'll see that 12.9 is the number there. And then the aluminum would be all the way at the last column on the same row. Yep. So you get 21.2. So if you ever forget, that's a good place to go back and pull it up.
That teacher must have had us highlighted, because I had it all highlighted.
Okay. Yeah, it's just 1,000 circular mills and 1,000 feet. Just lend it, easy to where you can just recognize the numbers there. But all right, so there's only when it comes to Ohm's law, there the voltage drops that you have there in series circuits, that's 100% loss of voltage. So if they gave you a bunch of resistors or some resistive type loads in a series type circuit and asked you what the voltage drop was, that's really a voltage loss question, and it's completely different from what we're talking about on this voltage drop question. So this is a parallel, just a standard, installed motor or whatever it might be. There's only really 5 real common system voltages that we deal with on the commercial trade, regular trade, and that's what this table is right here. It's a list of those 5: 120, 208 volt, 240 volt, 277, and 480, right?
Yeah.
Now, it doesn't matter to you on this particular number when we're talking about the percentage of loss that can occur, whether or not it's a single phase or whether or not it's a 3-phase. So for this part of it, this table will be the same number for either system. So that's why I've got all 5 of them on the same chart, the 120 all the way through the 480, even though that these two down here, actually these last 4 could be single phase, or these 2 could be single phase or 3-phase if you're talking about a 208 volt or 240 volt 3-phase system. But 277 volt would definitely be a 3-phase, so would 480. But either way, these numbers, there's only, out of those 5, there's only 3 percentages that by code we are allowed or use this voltage drop formula with, and that's going to be either a 3% branch circuit or 2% feeder circuit, or 5% for both combined.
Yeah. Okay.
And so the values, and the values that you're looking at here are the numbers you'll use every time. If you're looking at these 2 formulas right here, you see the VD right there where it says voltage drop. We look at it as a 3% loss, but it doesn't mathematically mean anything until you actually apply this 3% against one of these 5 voltage values. Because what we're trying to plug in there is a real actual number that represents what that maximum amount of voltage drop would be allowed to be, or if we're looking for it, that'd be the most that we'd want to see as an output on the formula. So when you use these formulas up here, that anytime you have to plug a number in for this VD on the bottom here if you're looking for wire size, or if you're looking for one of these bottom 2 values down here, either the maximum current or the maximum length or distance, if you have to plug some number in right here, it's going to be one of the numbers that you see on this table.
Oh, okay.
So you go back up at the top up here, we're looking at this test question. They give you the amperage, they give you the wire size, they give you a little bit about this motor. But the things that we need to solve for, if they're asking me for the maximum length, right? Maximum length is going to be this D down here, which is the black circle, which means I need to know what the voltage drop percentage is. I need to know what the wire size is, and I need to know the constant value, which we just got through talking about, and I need to know what the current or the amperage is of that those conductors, or the demand on those conductors. So in other words, if I get rid of this little D right here, and I just have these 2 figures here and these 3 down here, this voltage drop would come off this table based on whether or not that motor is a 120 volt, a 208 volt, 240, 270, one of those 5 values, right? And as a branch circuit, it's going to be this maximum loss of 3%. And they could even tell you, in fact, this one does tell you, this maximum length conductor for this install, where the maximum voltage drop is kept to a maximum of 3% drop.
Which it's not a code, but it's actually recommended, right?
That's right. Yes, it's absolutely. It's not an actual requirement, so to speak. It's more of a by the way, this is a damn good idea if you're doing, especially motors or inductive loads, which don't do well with voltage losses. They'll heat up the windage pretty quick on you if you had too much of it. And it's not an exponential relationship either. If you had a 2% drop, you may have an increase that's more than double what 1% would be, and then so on and so forth. So it's pretty quick rising steep curve there once you get past 10% is really the cutoff. If you get much more than that, you'll burn a motor up real quick, they say. But at any rate, that takes quite a bit to get a 10% drop, I think. But okay, so we're looking at the layout here. They give you, in this test question, ultimately they're asking me for this maximum length, and that's what this D is the distance in actual feet. And that distance there that we're talking about, I'm going to need to come down here and go down to another little deal here. Give me 1 second. Find it down here on a different page. I need to go back and recap a couple of these other things that should carry this a little further down here. I'm almost there. All right. So when we're talking about a distance, can you see this little picture here with the,
Yeah.
okay. That's the physical separation from this last overcurrent protection device to that actual piece of utilization equipment, in this case being the motor. So that 3% is what we're going to lose from here to here. And then we can't have more than 5% total is what the code recommendation is. So we take kind of as a, we kind of take it by doing the math on our own. It doesn't really say that in the code book, but we take the 2% as a net difference between these two figures here. But either way, we generally refer to this as the feeder percentage, this 2% being the maximum permitted for the actual feeder loss, and then the 3% being the maximum for a branch circuit. The two of those can combine being 5% for the maximum, no matter what you've got in between it from the start to the end. The longest furthest distance can't be more than 5% total loss. So, all right, and now that the K value is 12.9 for copper or 21.2 for aluminum. That's what this little box down here has, and it'll always be one of those two. It won't be anything else. And if they don't tell you for one way or the other, whether it's copper or aluminum, you'll have to assume that it's copper. And that's not only a PSI deal, but it's also a code reference from 110.
I think I've read that in hundreds of books and YouTube videos. Okay.
Okay, yeah. Oops, sorry about that.
I assume it's copper. Okay.
Yeah, it's actually a code from 110. I want to say 110.3 or something. It's the very, very front of the code book, but all right, so it's 110.5 is what that reference is for the link there. All right, so you're set on all the basic stuff here. So if you can remember this two kids on the block and the voltage drop and circuit mills on the bottom, this is going to take the place of the old school way of writing down these formulas just like you see here. And this is the same. Huh?
Those are really confusing. It seems like, the old ones. Yeah.
I think so. And not only that, you have to kind of memorize them all, because there's not an easy way to, I guess, as long as you can remember the first pair, what you're looking at is the other pair, which is the length of the amps. If you swap them top and bottom, these two look the same. They just swap the value on the outside of the equal sign with the bottom on the bottom value. And these just flip that formula upside down. But that's still, even if you look at it, that's kind of hard and confusing to memorize, where this little circle is kind of clean and simple. It's two kids over the voltage drop and circuit mills, and you just simply,
we're
going to do it right now. Well, we will a little bit. Voltage drop for the Texas exam is not that big of a deal, and that's why I'm kind of covering them with you as separately.
Oh, okay.
Not because I'm worried about you, not because I'm really worried about you having more of them, having a ton of them on the test, but because I know that for the Texas guys, we just.
It seemed like on our Utah PSI, I was just like, wow, are these voltage drop questions going to end? There was a lot of them.
Well, then maybe it's a good thing we're covering them good details. So this you'll get a little bit of review in class though too. So we cover them for sure. I just wanted to make sure you got a special kind of review. But all right, so let's say that we're looking for the distance, which is what we're looking for now. I always have to solve for a bottom variable, and so the only two bottom variables I have in this yellow circle are the voltage drop or the circuit mills. And so the distance isn't in here. It's up here on the top, but it has to be on the bottom to solve for it. That's where the black circle comes into play. So if we go back up there to the top, we had the same circle that we had before, but basically it flips upside down. The distance is on the bottom of that formula there. Let's say I just had it right there. I just passed it. I'm going to have to just copy that page and bring it a little closer so it won't be so hard to find. There it is. So we're actually going to have to solve using this formula because the D is on the bottom here. I'm just going to go in here and just erase the value that I'm looking for. And what I'm left over with is the formula that I'll use. And this relationship still stays the same. I'm going to take the top two values and I'm going to multiply them against each other. And I'm going to take the bottom values, multiply them against each other, and I'm going to divide that into the top value. So I'm going to do this line here is the multiplication. This line here is the division. I'm going to do all the multiplication first. Well, so you go up here and you look at this test question. They've given you everything you need except for, it seems like it appears that you're missing your voltage value, your branch circuit voltage value. Again, the first value that we're going to plug in here in this circle is this VD. But I can't plug anything in for this voltage drop unless I know what the voltage for the branch circuit is, because if I don't know what that is, then nothing I can do with it until I know what it is. So in this particular question, they've given you enough to solve for that just by giving you the FLC of that motor. And let me see if I can make this thing really more user friendly for me. They give you the FLC value of that motor. Now, is there somewhere that you can think of in your code book that an FLC value and a horsepower rating might be able to give you a branch circuit rating?
Let's see. It's something to do with 746, right? Or let's see. And that was the confusing part on them voltage drop questions. I didn't know when you're dealing with horsepower, if you timesing by the 746.
Yeah, I tell you that the thing about the 746 is it's got just really absolutely nothing to do with these calculations. I don't think yeah, you can't really use in fact, when you're sizing conductors and trying to size a demand load for branch circuits and whatever, for motors especially, specifically in the 430, they give you a requirement to use the table values that are listed under 430.248 and 250 on page 350 and 351 of your code book, to use those demand values that are calculated with the FLCs listed there. So if you look on page 350, you see two tables on page 350. One of them is 430.248, which is the first one on your left-hand side of the page. Okay. The larger table that's on the right-hand or the inside set, you can X that out because that's a two-phase AC motor, which is something I've never personally. I know what they are and I've heard about them, but I've never actually seen one. I don't really know that I've ever seen any two-phase system in existence other than just in a book now, history book basically.
Okay, I'm trying. So I see 430, 248 full load currents and amperes single phase.
And that's a good table.
Okay, and then 430, 250 full load current 3-phase alternating current.
On page 351, yeah, those are the two tables. The one that's on page 350, that's 249. You can X out 430.249.
Okay, I'm trying to see what the hell here. 430, 250.
Well, are you on page? You have just a regular code book, right? Not a code book. On page 350, do you see two pages, two tables?
So it's is it 430, 249? Is that what you said?
That's right. Yeah, put an X through that with your highlighter.
All right, that's the squirrel cage deal, right? Okay.
No, with the one on the 430.249 might be an induction scroll cage, but it's really what the issue is, that it's a two-phase system.
Oh yeah, I see what you're saying there.
Yeah,
two-phase. Yep.
So what you're going to use for this test, and pretty much in the trade even, is going to be the 248, which is on the left-hand side at the smaller table there for single-phase motors, and then your three-phase table will be the one on page 351 to your right there on the top.
There, I see it. Okay, yeah.
All right, so
I don't think two-phase, that doesn't work. Okay.
Yeah.
Right.
So what we're looking at here in that test question is they give you the 13.2 amps on the FLC value, and they gave you that it's a 2-horsepower single-phase motor. So they give you enough info that you could go backwards and reverse look up what the voltage is. And so the long story short, on the single-phase motor, which is the smaller table on the left-hand side of page 350, on the 2-horsepower line, just follow it over until you find that FLC value, and then look at the column that it falls under, and that's what the branch circuit voltage is, which is in this case 208 volt.
Oh, okay, 208. So you're at 13.2. Okay.
Wow. So it's kind of a nice way of making you really look at that, an example that could actually happen to you, where you knew what an FLC value or a demand on the conductor, didn't know what the branch circuit voltage was or whatever. I mean, that probably wouldn't happen to you in the field exactly like that, but you get the idea. It's a pretty good way of making you really kind of look and think about it. But all right, so the first value that we need in this circle, if we're solving for this distance, and that's what we're looking for with this maximum length conductor, is this distance. And so this little smaller circle here, I took the D out, took the liberty of doing that. So what you're left at in this question is this circle right here with these values here, and I'm looking at this voltage drop as the very first value I have to plug in here. Well, now that I know that this 208 volts is my branch circuit voltage, and then I'm dealing with a branch circuit which is no more than 3%, I've got something I can start with. And this thing I always tell people is that, let's just say that if I told you that if you passed your test, I'd give you 3% of my annual salary as a reward. That might sound like a pretty good deal if until you know what I really make, and then it wouldn't be a good deal at all, because 3% of my annual salary is not going to be much money.
Right. Yeah.
So, but that value, though, the instinctive value is not the 3%. The value is what it is represented against whatever the system voltage is. So I'm going to take 208 volts, and I'm going to cap my loss here. That's where this table comes into play. I don't want to lose more than that's actually 6.24 volts. Should be a 4 there. So at 208 volts, which is what my branch circuit is, at 3% on a branch circuit, I don't want to lose more than 6.2 volts.
Okay.
So that's what I'm going to plug in right up here for this voltage drop. Is I'm going to come up here and I'm going to put in that actual value that I'm looking for as far as a fixed in place, so 6.24 volts.
Okay.
That caps my my losses there, so to speak, and then that's going to give me that little quadrant. And the next thing I need is circular mills, and circular mills is just a mathematical value for what our wire sizes are in a circular mill context,
which is in the back. Okay.
That same page that you were on just a minute ago with the table 8, chapter 9, table 8. You'll find your circular mills there, and for number 12, it's 6,530. No, 6520. Is it 6520 or 6530?
Going there right now.
Page 767, I think, isn't it?
Yeah, or 766. So you go down 12 would be 6530. Right?
6530. All right, so 6530 sounds right to me too. So that's what goes in right here is 6530. And that is my circular mills for number 12. And again, I'm getting that straight from what they gave me in the values up here for this test question. It was a number 12 conductor.
Before I go too far, if you went back down to your table that you were saying about, right there, the 208, the 6.2.
Mm-hmm.
Now, is there a way that they had you figure that out, that 3% out before, right?
Yeah, I just took this 3% and multiplied it against each one of these values, and that's what these are.
That's right. Okay, so you've already done the math.
Yeah, that's right. It's just a shorthand way of doing the math, and then also having a value to plug in, because sometimes that voltage drop, if you're not prepared for a question like that, and they throw something at you, you sometimes forget to do this conversion or don't know how to do this conversion for this voltage drop. So if you have this table to kind of fall back on, it'll kind of help prime your memory to go, okay, that's right. I just
have them all memorized, huh? Great. Yeah. So, okay. I see how you're doing that now.
Yep. All right. So it's nice and clean. It's kind of an easy way to kind of keep it in check, I guess. But at any rate, that anytime you get to plug in something for a voltage drop, either on this yellow circle or over the black circle, either one is going to be that same table, unless that's what the value that you're actually looking for in the beginning. So, all right. So I want to multiply these two numbers here against each other, and then on the bottom, I'm going to have 2 times 12.9. Because it didn't tell me one way or the other on that copper or aluminum. So I'm just going to do 2 times my constant, which is 12.9 for copper. And then times, now this is a little trickier, because to really do this test question correctly, I need to talk about continuous duty, but I don't want to do it just yet, because it's probably just going to give us a whole nother section to just get off track with. So I'm just going to leave it the way it is right now, just at the value that they give us for this demand on the conductors at 13.2, but that you'd actually have to worry about this motor being a continuous duty load, which would make this number higher after we do the adjustment for continuous duty. But for now, let's just say that we had a non-continuous motor that was 13.2, which would matter to us one way or the other when it comes to size and the breaker size, but it would matter to us with the wire size, which is what we're dealing with. But at any rate, I'm just going to skip that and just leave it at 13.2 amps just for this voltage drop.
Okay.
Yeah. All right. So we're looking at 13.2 amps. 12.9 is a constant, and then the 2 being the double for the. Basically, what that 2 does is that 2 doubles the distance, right? So if I'm looking at a motor circuit, a branch circuit for a motor, what I'm looking at is, well, let's see here. I thought I had a better example up here. What I'm looking at is I'm sorry, it was further down on that other deal here. Hold on one second. I'm sorry about that. Started and stopped my sentence like 3 times now. All right, so I'm looking at this percentage, right? And on this branch circuit, which is maximum 3%, I've got a total distance of physical separation of these two, but I also have the total length of conductor, which is going to have one wire going to the motor and one wire coming back from the motor
to make it work for 120.
Yeah, I mean, I gotta have a complete loop or a closed circle there for my electricity to flow. So I'm either going to have to.
Yeah.
I mean, with a single phase motor, I'm going to use the line side and the load side, the neutral or the grounded conductor, which is the proper term for it. I'm going to use those two wires with the same line current or load current branch circuit values coming back. It's going to be one wire there and one wire back, or if it's a single phase 120 volt, excuse me, as a 2.8 volt single phase, I'd have a black and a red, so I'd have two line values going out there, but I'd have one wire going there and one wire coming back either way.
Yeah.
So
the only time you need to worry about that is when they tell you it's a 3-phase, right?
That's right. And the only difference there is you're just going to swap that 2 in the formula for a 1.73, and that's the only difference. Everything else stays exactly the same. Mechanics, the table, voltage drop values, all of it will be the exact same number. So that's really kind of makes this
1.732. Okay, yeah, for 3-phase. Yeah, right. Okay.
So, hi. Yeah, no problem. Hi. How are you doing? This is my lovely young ladies. Say hello. She can't see. So.
Hello.
Can you see her?
No, I can't see a picture at all. Dang it.
Oh, you can't see the video?
All I got is your tables. Maybe I shut the video off.
Oh, you shut the video off? Oh, I look so handsome.
See a picture of me? Or?
No.
Okay.
Well,
I probably turned the video off.
She's really cute. It's too bad you're missing
out. That's great.
All right. Anyway,
right.
well, I've got this recorded, so I think you can. I can email it to you later. As a matter of fact, if you want to watch the video part of it, you can come see the dog. He's right there. She's right there. Want to get down and pet her? Yeah. I don't know
how to turn the dang video on. I should have figured.
It's on. I just don't know how you'd click on it. Do you see a little window with my name on it or anything?
Yeah, there's one way up at the top right, Mitchell. Estrell or ST?
Yeah. Well, that's on your. Let me see. I just started.
Oh, there you are. Okay, I see a picture of you now with your headset on. Yeah.
Okay. Yeah. All right. Hold on. Let me see if I can get the lift her up again, babe. Say hello.
Oops, I'm sorry.
Say hello.
There she is.
There
she is. Hello.
Yeah, she's staring at me.
Yeah,
hello.
Beauty. How old is she?
Hey, she's a little bit over a year.
Oh,
yeah.
Nice.
Yeah. She's a mess, I tell you. She's just a hot mess. That's okay, just leave it, babe. Just leave it, babe. I got it. Don't worry about it. That's all right. No problem.
They're another full-time job.
Ooh, boy, I'll tell you what, you're not kidding there. And we're 6 months pregnant, and you're gonna have another a girl.
Oh, cool.
Yeah, we were looking for a boy the first time, and looking for a boy the second time, and both times we're gonna end up with a girl on both times. So it's
I got married late. I got married late, and my wife can't have any, so we might have to adopt later. So.
Well, you can always borrow mine. We could do some kind of loan program or something if you'd like.
There you go. That'd work.
Yep. Yeah, she's a joy, but she's definitely a handful. She just literally today is the first time she's really walked more than one step at a time by herself. But today she walked about 6 or 7 steps alone, unaided. And that's kind of scary. Yeah, it's hard.
It'll be coming soon, huh?
Yeah, we can't keep up with her as it is now when she was crawling. So it's a nightmare. Okay, all right. So what we're dealing with there is that 2 just doubles that distance. So in that question that I asked you, the way I asked it was I actually asked you for the maximum length of conductor, which is going to be basically what double our answer is, because this formula that we're using measures the distance, which is just the physical distance or the physical separation. You okay, Mama? Sorry about that. Dog just fell over off my lap. Yeah, all right. Just fell over into a ball of her bowl of water. Or I hope that's water, not pee. Better not be. All right. Anyway, all right. So the formula gives us the physical separation. If they ask you in a test question what the distance of conductor, the length of conductor, excuse me, not the distance, but the length of conductor. Which if you go back up here and look at this, what I ask is what's the maximum length of conductor for this installation? That's actually going to be twice that distance because we've got one wire going out there and one wire coming back, right?
Oh, okay. Yeah, and I always wondered how they got the two involved in that. Okay.
Yep, and that's what it does, is it doubles it. Now, I suppose you could probably take that 2 out. No, you'd have to double that double. You'd have to do it 4 times.
Okay.
You know? Anyway, so regardless of one way or the other, that distance there is going to be the physical separation. And sometimes they'll ask you for the distance, and sometimes they'll ask you, like in this case, what that length of conductor is. And if they ask you for the length of conductor, you got to be real careful to make that little switch between the two in your mind and make sure that you're answering the right value. And that the Colorado Masters, all of the voltage drop values or voltage drop questions they had were always asking for the length of conductor, and or sometimes they would ask for the distance. So you kind of had to pay attention to which one they were really ultimately asking you for. Okay, so since we're looking for the maximum length of conductor, we're going to take.
How do you? Sorry, Mitchell. I was going to ask you.
Yeah.
How do you tell between the two if they're asking for the length of conductor or the distance?
Well, if they just ask you literally just the wording, if they ask you for the distance, then it'll just be this formula without anything else worried about. But if they ask you for that length of conductor, then you're having to consider that length of wire that goes out there, and then the length that comes back, which is twice what our distance is.
I see. Then it involves the two. Okay.
Yep.
Right.
Well, no, the two is the distance. So the way that this formula is set up is that it's going to give us the distance, which is the physical separation. And then if you're looking for a single phase branch circuit wiring, you're going to have twice that number because you'll have twice the amount of wire that's twice the distance. Does that make sense?
Yeah.
So you'd have a D value from this formula that would represent the black wire, for example, and the D wire that would represent the red wire in a 208 single phase. Something like that. So, all right. So let's just plug in the values here. So I'm doing voltage drop here. I'm down here at the bottom. We've got all the numbers, in now. I'm going to take the 6.24 and the 6530, which is the voltage drop up here in the circular mills. I'm going to multiply those two numbers together.
Okay.
Let's see here. I've got a calculator somewhere, I'm sure, on this. I tell you, I do not know how to work this this Windows 8 stuff at all. And what's even worse is that I learned how to do Windows 10, which is the version after this that they're doing a live, like they're doing an insider review on, and I figured out how to use it, but I'm still struggling with this Windows 8 stuff.
They had a Windows phone that was pretty hard to figure out too.
Sean, it's not intuitive by any means. So there we go. That should put me back on where I was at. All right. So calculator wise, I'm looking at a value of. Let me see if I can do this.
Probably here too. 6.24.
So you can still see. Can you see both my screens now?
Yeah.
Okay. All right. So I'm going to take the 6.24 and I'm going to multiply it against 6530.
Okay. Gives you 407, 447. Right?
Yeah, it's 40,747, and that's the top two values multiplied against each other. And then I'm going to take the bottom values and multiply all those values against each other, which is the 2 times the 12.9 times the 13.2. So these two right there end up being, let me get this out of the way here. These two end up being 40,747.2. And then we're going to take that and divide it by, kind of hard to do in that side this the way I got this little circle drawn. Sorry about that.
It's all right.
We can get rid of the circle and just write the values out there. That way it'll make a little bit more sense there. All right, so you see them up there at the top, 60, and these equal that top number. And then we're going to do the bottom 3, which will be 2 times 12.9. So let's do clear And you know, after a while, and this is probably something that if you're liable to do several of these types of problems, I would go ahead and do the math on this as well. And I'd write down 25.8, because 2 times 12.9 is going to give you the same steps repeatedly. If you're dealing with copper on a single phase type voltage drop question, it'll always be 25.8 when you're done with the math. So really, instead of memorizing 12.9, I'd memorize 25.8, and then the other one is 42.4, which is 21.9, no, 21.2, excuse me, times 2 would give you 42.4. So 25.8 and 42.4 is what that first step is going to be mathematically every time. So it'll save you a step. It'll make it a little quicker with them if it helps. If that confused you, then just ignore what I said. But at any rate, 2 times 12.9.
Okay. Sorry, go ahead.
Go ahead. It's 25.8, and then times 13.2. My bottom value is going to be 340.56.
Okay.
And so that's the bottom number that's going to be divided into this top number, and our math is almost done. We'd take that 340.56, and that line down here means I'm going to take this bottom value and divide it into the top. So this 340.56 divides into the 40,747. So
0.56 divided into 407, all right, 47. Would you put the whole number in, or 0.2, I guess? Okay.
Yeah, I'd go ahead and just leave them out the way I've got on the decimals. It'd be 47.2 and 340.56, and I just divide the 2, and that gives you a value of 119.647. And the PSI doesn't look at any number past the second significant digit. So what you're looking at here, really, this 7 that's on this decimal point doesn't round this 4 up. It's just simply going to be 119.64, and that's going to be our number there.
Okay. Yeah, you can usually tell right in the test question what the answers, if they round it up or down. Usually.
Yeah. Yeah, rounding up and rounding down based on the 0.5 is sometimes can get you in trouble, because if you're dealing with a maximum calculation, then it doesn't matter if it's a 0.9, you're going to have to round it down, because maximum calculated values are just that. If you round them up, then you're going past your maximum calculated value, right? Yeah. So in this case, we're looking for the maximum calculated length of distance here, or the distance, not length. So that 119.64, if we're doing any rounding one way or the other, we'd always have to round this type of formula down. So my whole number would be 119, not 120.
Yeah. Okay.
So 119 feet would be the maximum number of feet. Now, since they're asking me for the maximum length of conductor, if I've got a distance of 119 feet, I'm going to have 238 feet worth of wire, running 119 feet running to the motor, and 119 feet running to the other on the other wire. And so that's the answer to your question. It would be 200, double that number, 119.64 times 2.
Okay.
Which, again, since we're dealing with a length or a distance in feet, I'm just going to make that 119, because I would round it down, and then I'd have another 119 feet for the other wire, which together would end up being 238 altogether.
All right.
Does that make sense?
Yeah, it's just so dang confusing trying to remember all that.
It is. I tell you, this is, and I don't expect that the first time I did this that it'd be easy. But what I did want to do is make sure that you could at least see the concept behind these little circles.
Yeah.
And if you can grasp the concept of these circles and give them a little bit of practice, I think you'll find that at least this part of it will be easy for you, as far as remembering what the formulas are, remembering which one to use, and kind of how to get started. And so those two formulas right here, and then this chart right here, used to be you could put them on page 766, because there was a little bit of room there next to that table 8, but now there's not. So, but there's not. There's a little bit of room, or a little bit of space under table 5A, which is just there, I think, to the left of table 8, isn't it?
Yeah, table 5.
See that space is on the bottom of page 765?
Yep, exactly.
So I'd put those two, the two kids on the block and then the mirror image of it and then that little table right there. I'd put those on this page and then my notes to copper being 25.8, aluminum being 42.4, and again those being single phase copper, single phase aluminum.
Okay.
And
Are
then
you going to go over that in the class, or I mean, well, I guess I could do that when I get done or something.
yeah, I'm going to go back. We're going to do a couple of Ohm's law, a little bit of Ohm's law here in just a minute, and then I'm going to go back and we're going to do a couple of practice questions with these. And what I'm going to do is, I think it's always good to kind of do a couple of them while watching me do a couple of them. At least just kind of try to follow my steps and not really worry about whether or not you understand them or not, but just can you follow the process? And then once you get used to seeing the process, then if you try a couple of them on your own with me kind of in the background, kind of helping you with each step, then that helps, the steps actually kind of makes more sense. And then once you've learned the process and then learned how to do the steps yourself, then you should be able to duplicate that again, and on your own on a test pretty easily. And I've always been much more on the mechanics of stuff than I am about formulas and this and that the other, because it's nice to know all this theory and it's nice to know what the formulas are and stuff and kind of how to modify them and whatnot. But the truth is that that's not going to necessarily get you through the test, and you've got enough on your plate to worry about as it is. So if we can simplify any of the processes and turn them into mechanics, you can duplicate mechanics. I mean, if you got a recipe, you can cook just about anything somebody puts in front of you, as long as you got a pretty clear recipe on how to do it. And that's what I'm trying to do here, is kind of give you the recipe so you can just kind of follow them, lockstep, when you run across a similar type question. So I'm going to need to take just a 5-minute break, if you don't mind, just to kind of
go ahead.
the drink, and then I'm going to give you I'm going to give you one to work on your own real quick. That way you'll have a little practice one. And let's see here. And then when we come back, we'll do some the Ohm's law stuff. Back down the voltage drop here. If we had a here we go. This is going to be what we're looking for. I'm going to close this navigation window. There's that same question, but with just a little bit different. That's a good one. That'll kind of give you a good idea. You can do either one of these if you like, or you can do them both. But can you see both of the 3 and 4 pretty easily?
Yep, 3 and 4. Let me write that down. 3 and 4. Okay. Yeah, I can see.
That'll give you a couple of them to do real quick, and I'm just going to make them just a little bit bigger. So that'll be a little bit easier to see. Let me get this out of the way. All right, so 3 and 4 there in bigger print, and then I'll be back in just a bit.
Okay.
Thanks, sir. I'm just going to leave this open, so you just won't see my video, but it'll still be
all right
live. Hey, go. These one more. I just spilled most of them. I just like that, man. I like that. Yeah. Hey, the beauty. Hang on. Maybe 4 mile put that on.
Enough over here. Huh? You turn that down low. Where's the dog at? Two. Okay. And to the 100. Times 390. Right. This one, 2 times. Oh, okay. Oh, 0.9 times and that's what you want. Times your distance. Are you there now, Mitchell? Length 275 feet. Five. So if I go it's way hard. Okay, that's better.
All right, I'm getting back. Are you still there?
Yeah, I'm still here. Can
That's
you hear me okay?
Yeah, just fine. Yeah, absolutely.
Okay, I put on my headphones here, the headset thing.
Were those pretty easy for you?
I don't know if I got them right. I'm kind of forgot your formula, so I went back to my formula, and I liked your way better, but I don't know if I got them right.
All right, let's see here. We've got, we'll start with a squiggly line here, and we'll do the outline in yellow. All right, can you see that? No, it's not very bright, is it?
Barely, yeah.
That's kind of hard to see, so let me make a brighter color here. Draw in maybe red will be easier to see. Yeah, there we go. All right. So I'm going to look at, first of all, ultimately, what is this question asking me to do here? I'm looking for the maximum size conductor required to stay with the voltage drop. So the wire size here is ultimately our goal. And we are in a Wire size is going to be the first circle that we had, which is the 2 kids on the block, 2K ID on the top. And I always have to solve for bottom variable. That's why I'm using this one, because if I'm looking for wire size, it's 2 kids on the VD circular mills on the bottom down here. So I'm looking for this right here. This is my question mark. That's my unknown value. Voltage drop being right there. All right, so the first thing I do is I look up here, and they tell me if it's copper or aluminum. A single phase, same setup we had before, so we know that this is a 208 volt by looking it up, because we looked it up earlier. So it's 208 volts.
Okay.
And
right.
So we did a reverse search on that and did get same to that 275 feet. So I know that my D here is 275. I know my I is going to be this. Again, the answer here, the truth is this 13.2 amps. You know, the continuous duty is a concern that all has to do with wire, and sometimes guys get it mixed up and try to use it as a breaker, multiplier and things like that. Continuous duty is what the whole reason for us having to deal with it is that after about 3 hours, and that's what the code kind of gives us, is that cutoff period, 3 hours or longer. The conductor under continuous use like that is going to build up a little bit of heat load, and that heat load on that wire is going to actually create a little bit more resistive, values from the conductor with same things being constant, and so that tends to then turn up the heat even more so on the wire, and so you have this situation occurring that after about 3 hours, the demand actually on that wire is a little bit more than it actually was before then, or if it was not, on for 3 hours, So if there was ever a time that continuous duty came up to play and needed to be concerned with, this is exactly the situation. Because if a voltage drop is a problem over 200 feet, 275 feet with whatever size wire we've got that we're looking at, it would be even more so in 3 hours because the load's going to be worse, right?
Yeah. Yep.
So really this motor being, and motors on your test are going to be considered continuous duty unless they specifically say otherwise, especially on something that's 2 horsepower. So I'm going to look at this thing as automatically being a continuous duty issue. So I'm going to take 13.2 and I'm going to multiply it times 125%, which is what we use for continuous duty calculation elsewhere in the code book. So 13.2 amps. Okay. Yep. Is going to be 1.25, and you can actually find a couple of references to that in 430, 430.22 being the controlling one there. But this math here is really what I'm putting in for this I, because my demand on that wire is actually a little bit more than 13.2 at the end of 3 hours, so it's really going to be probably, I think, 16 and a half is what it comes out to be.
Okay.
Let's see here. I need to bring my calculator back up here.
13.2 times 1.25, right?
Times, yep. Yep, that's it. So
16.5, okay. They made us do that a lot in classes.
Yeah, you get used to it. But now I didn't do it on that first example because I didn't want to overload you with too much. So that's why I left it at 13.2. Yeah. But you got to remember, if there are any kind of indication that it's a commercial lighting of any kind, whether it's outside, building lighting or signage or something of that nature, or if it's any kind of commercial, occupancy that might have to do with lighting, that's always going to be continuous duty. Even if they told you it wasn't, it'd almost be impossible to not argue that it would still be continuous duty factor, because there's just no way you would consider a commercial building to be open for 3 hours of business or longer, at some point in its career.
Yeah.
But at any rate, the other list of things to watch out for are water heaters that are tank type, 120 gallons or less on a branch circuit calculation. So any kind of water heater, you just got to be careful of that. Water heaters, and then also fixed in place electric space heating would also be continuous duty. So any kind of branch circuit calculation that dealt with voltage drop on either of those 3 examples, motors being the 4th example, I'd watch out for that. They're not necessarily going to make a big deal out of it, but you still have to take it. So one way or the other, this 16.5 amps is really kind of what we're looking at the end of 3 hours on this problem here. So because of that factor, we're going to take that I value and plug it in at 16.5, not at 13.2. So that comes in at 16.5. And you wouldn't have gotten that on your own because I didn't really tell you about it. So, don't feel bad if you didn't do it. This might be why your answers don't come up exactly right. But at any rate, I'm going to be interested to see kind of if you get your other values in. So at 16.5, that's going to give us a math problem on the top line here that's going to be 25.8 because 2 times 12.9. This K being 12.9 for copper. And those two multiplied against each other, like I said, will always be 25.8. So it's a good number to just kind of keep in the back of your head. So 25.8 times 16.5 times 275 will be my top line number there. So 16.5 I already got on the case. Go ahead.
That 25.8. It's always the same.
That 2 and that K that are there, right? If this K is a constant that doesn't ever change except for the wire, metal makeup.
Yeah.
I'm going to have either 2 times 12.9 or I'm going to have 2 times 21.2 every single time. It'll be one of those two on single phase. So the math on these two, if I know that it's copper and I'm dealing with single phase, when I do the math of these two numbers right here, it comes out to this 25.8 every time.
Oh, okay, gotcha. That's where you're getting. Okay.
I'm just saving a step is all I'm doing. In other words, I'm rewriting my equation as really 25.8 instead of 2K. But it could be
gotcha.
It could be 42.4, which is the other number, which is what 20. That's right. Okay.
Perfect.
Anyway, so that's a shorthand. But like I said, if it messes you up, don't even worry about it. I'd rather you skip that than let it mess you up. All right. So 25.8 times 16.5 times 275 is what we're dealing with here. So 25.8 times 16.5 and times 275 feet. And D will always be listed in feet. So I like to use D instead of L because L makes me think of the length of wire. D is an easier number to keep it straight. The D is a distance, not a length of wire. So, it's either one, it's in feet. But that gives us on the top line there 117,067.5.
Okay.
And again, I'm not rounding up or anything. I'm just going to leave these numbers the way they are until I do my division. And then the bottom two, I'm looking for this one right here. So the only thing I have to plug in here is going to be this number right here. And I know from our previous discussion that 208 volt at the voltage drop recommended guideline for a branch circuit is going to be 3%.
3%.
Yeah. And it's 3%. So if I take 208 and I multiply that times 0.03, 208 volt times 0.03 on my calculator, my maximum amount of volts that I want to lose, if I put my meter at the breaker and then I put my meter at that motor, the most I want to lose is going to be 6.24, I think. So 208 volts times 0.03 gives us 6.24 volts, and that's the most in physical actual volts that we want to lose. So what this does is that this caps our formula as this being the maximum amount that we can lose there. So when I plug it in over here, that's going to force this number here to compensate to this exact value. So when I divide this 117,067.5 by this 6.24 volts, that's going to give me, let's see, if I just times it instead of dividing, let me see what this does. 117,067.5 gives me 730 circuit mils. That can't be right. So it's 117,067.5 divided by 6.24. 18,760 circuit mils is what I came up with. Does that sound about right to you?
Yep. Yeah, and I followed along with you and punched it in my calculator. That's what I got.
Okay. And again, this 7 up here, this 817, I'm taking the 7 and I'm just dropping every bit of that. I don't even care about it. I'm just looking at the 81 being the two significant digits after the decimal.
Oh yeah. Okay.
So they're just gonna take that 81 and be done with it. So it's 18,760.81. Regardless of the fact, this is a minimum calculation, which means I got to have at least that many circular mills in a wire. So I'll always round these type up, even if it was 0.01, at round up to 18,761. Does that make sense? where the maximum length was a maximum calculation. This is a minimum wire size, so we're going to have a minimum of 18,760 circular mils. So we go back to 766 on Chapter 9, Table 8. That third column on the page there, the third column gives you circular mils all the way down to 250 kc mil, which at that point it goes to blanks because we express them in circular mils after that anyway. So 18,760. A number, let's see, from memory, I'm going to tell you what it is. 10,380 for number 10, 16,510 for number 8. So it'd have to be a number 6, which is like, what, 24,000 something?
Yeah. 26,240.
26,240. So we missed the, the number 8 by a little bit, and we're way away from a number 6, but I mean, that's just the breaks. We'd have to have a number 6.
Yeah, number 6. Okay.
So that motor,
that
motor at 13.2 amps, after it was all said and done, that 13.2 amps ended up costing us a number 6 conductor. By the time it was all said and done.
Wow. Okay.
But does the mechanics of it kind of make a little bit more sense?
Yeah, it does. Yeah, I got to the end of that and I thought, God, I should have a number to figure out the circular mils, and I didn't the way I did it. So
what'd you end up getting just on your circular mils on your equation there?
I chose the answer number 3. Cannot. I was way off.
What was your actual numbers though? Your math on it?
It's what I did is I did it the way with 2 kil.
Okay. 2
times the constant times the amps times the feet. Right. Yeah. Times the feet. And then I think I might have stopped right there.
No, that's fine.
Okay.
I'm just
2 times 12.9. Is that what it is? Yeah, 12.9.
Yeah.
12.9 times the amperage, which was 13.2. But I actually, no, because I didn't. Because I went back to remember what you said before, find the 208 on the motor part of it.
Okay.
But I can't remember what I really did.
That's fine. 2 times 12.9 times 13.2 times 275 feet, which is what you would have done without knowing about the continuous duty, would have been 13.2 times 275 feet. So that's the top of that little circle is 2 kids on the block right there. 2 kids. Yeah. And then the bottom part would have been the voltage drop. And again, I would have gotten this straight off the table.
I got 93654 on that. Okay. Yeah. After I multiplied that off. Okay.
What'd you get on it when you were done?
It was 93654. Yeah.
Okay, all right. Instead of the 119, yeah. Now that's not bad. That if you got that's the mechanics of it, and the mechanics of it are more important. And right now, the mechanics are way more important than the actual finesse of the final answer. We can always.
And then I got frustrated right there after I found that number. I thought, oh hell, I'll just turn back to Chapter 9 and find it in the circular mils, and that's number 10.
Okay, well, so you had how many circular mils did you have total?
93654 is what I went off of. I ended right there. I couldn't figure out what to divide that by. 2 kil.
Oh, I got you.
Your circular.
I got you. Okay. All right. So you had the top number based on 25.8 times 13.2 times 275 feet, I guess, right?
Correct. Yep.
So 93,654, and then you just didn't know what to do with this number.
Exactly. I was stumped right there.
All right.
And I knew there was something I needed to divide by, right?
This little table right here is and that's why I did this little table. It's because if you're looking at this, little circle, this little yellow circle here, this we have to solve for a bottom variable. So in this case, we're looking for wire size right there. So it's going to be these numbers, which is what this 93,654 represent, and then this voltage drop right here. Anytime I have to use this in the formula, I come down to this table and I pull the value off this little chart.
There you go. Okay.
Make a little bit more sense?
Yeah, exactly.
Okay. And so, and again, like I said, that's the only one on this whole table that I didn't carry out to the third place. So this is actually 6.24 volts. I need to go back and change that. But and so it is important to you to know if you're dealing with a branch circuit only, or if you're doing a feeder calculation, which is going to be 2% instead of 3%, each one of these numbers on the bottom would differ depending on whether or not you're dealing with a total, from start to end, which is this maximum voltage drop for both the feeders and the branch circuit, or if it's just the feeders, or if it's just the branch circuit. Most of the time they'll be pretty clear, and in this case it was a branch circuit. If it's a one breaker in the load right below it, then that's just 3% maximum on that deal. All right, so no, go ahead.
I was just going to say I could have found that if I would have threw 208 times that.
That's right, times 3%.
That's right. Okay.
Yep. You give it an actual value that it represents there. All right, so we're looking at, where did my voltage drop go? Where were we just at? Plans and prints, there they go. All right, so we had the second one, which was minimum size THWN aluminum feeder conductor, required to limit the voltage drop 3%, where you had a three-phase, 480 volt, 100 amp, non-continuous load, located 390 feet from a panel board, K equals 21.2. So this is a really good example of one that might even be worded kind of similar with that K value given to you like that, as you mentioned earlier. So I'm looking at, I'm looking for, what are they asking me for? And they're asking me for a wire size. Again, it's the same type of question that we just dealt with, because if I'm looking for wire size, that's what the circular mill is. The circular mill being a bottom value of the normal circle there, with the voltage drop being right here, and two kids on the block, or two kids on top, right? This case, this K value is going to be 21.2 instead of 12.9. It's non-continuous, so I know that this, I don't have to worry about taking that 125 like I did on the motor up here.
Oh, okay.
So that part right there just tells me that this 100 amps is what I put in right here is 100 amps. The distance they give me in feet is 390 feet. So I've got the top part already kind of filled out without even having to sweat too much. And that's 390 feet, 100 amps. I don't have to worry about continuous duty there. This is 2 times 21.2. which is going to be 42.4, 21.2, excuse me, times 100 amps. So 42.4, which is what these two multiplied against each other, times 100 for the amperage, times 390 feet. My top line there comes out to 1,653,600. And I'm dealing with, excuse me, I'm sorry. Excuse me. Put a brakes on it. Excuse me. This is a three-phase formula.
Oh, okay. I wanted to call it that, but I was thinking about it at the first.
Yeah, I should have, right off the bat, I should have recognized that. So it's not 2 times 21.2, it's 1.73. Thanks for catching that. Appreciate that. I know you were going to say it. You're just going to wait till I was done and then tell me, and then I would have.
No, I forgot about it. I honestly did, because I was going into the length and everything else. Okay.
Now you'd said something.
Went past it.
Yeah, you'd said something about 1.732 earlier. Again, since PSI just looks at 2 digits, we just do 173 instead of 173.2. It's not a significant number, but it's a difference nonetheless. So 1.73 then instead of 2, because when I have 3 wires working in concert in 3-phase, my load value is going to be less than what a single phase would have. So no conductor is going to have, so that's what this 1.372 is. It's actually a little smaller number than it would have been as a single phase. So I'm looking at 1.73 times 21.2. So 1.73 times 21.2 for the aluminum makeup of that wire, times 100 amps, times the 390 feet. That's going to give me a number on the top that's a little less. It's 1.4,303,364.
Wow, okay.
And so my bottom number that I'm dealing with, the voltage drop, I'd take the 3-phase into consideration right here, but this number won't ever change. That table that we've got that I kind of told you about, that table value is good for 3-phase or single phase, because if I were to do the volts down here times 1.73, I'd end up canceling them both out. If I do it on the top and on the bottom, it cancels out. So I just want to take it up here, and I don't want to take it down here. So in other words, this is whatever it is in single phase, it'd be the same thing in 3-phase in this little step here. So my voltage drop is going to be plugged in at, if I'm looking for a branch circuit, no, these are feeders, but they're asking you for a 3% voltage drop. So it's a branch circuit feeder conductor is what they're giving you, because they're asking you to limit the voltage drop to 3%. So this 3% is still going to be the same.
So it's 480 times for 3%.
Yeah, so 480 times 0.03. Again, on the table, we just look it up, but it's 14.4 there. If you do the manual calculation and then divide that number into the 1,430,364.
Okay. I'm going to do that real quick. 480 times the 0.3, right? One. Yeah, okay, got it. 114.4. Okay. Or let's see. Yeah, got it. Okay, divided that. Okay. Wow. Okay.
And I get 99,330.83 circular mils. I'm just going to make this 31 circular mils, because that's way less than what we'll end up with anyway. So we're looking at a wire just bigger than 99,331 circular mils, table 8, page 6. And I'm looking at, let's see here, I'm on table 8.
1-aught probably.
Yeah, 1-aught is yep, exactly what it is. 105 600 would be 1-aught.
Yeah.
So yeah, we missed the number 1 by quite a bit of margin. So we're pretty close to what that 1-aught would be anyway. So his size. Oh, I'm sorry. Yeah, that's right. Because the circular mils doesn't matter whether it's aluminum or copper. It's wire size is a wire size. Now your capacity going to be different, right?
Yeah.
But if we were to do this equation as 1.73 times 12.9, then the numbers are going to be less circular mil wise. But when you're converting it here, it doesn't matter to you once you've gotten to this point. The circular mils will be the circular mils, regardless of what makeup they are. So we'd have to have a 1-aught aluminum conductor size at 105 600 circular mils. All right. Okay. Let me work a couple of them out with you, just kind of watching, and so you can kind of get the feel for it in a pretty quick manner, and then we'll call it good and let that ride, and then we'll do.
Okay. Yeah, you're probably wore out. You're probably wore out after 5 or 8 hours.
I'm not bad. I mean, it's probably not as bad as you've had. I mean, it's tough to work out all day and then come in here and sit down and let your mind be fried by some stuff that you don't normally deal with either. So.
It's just remembering all. That's the dang hard part.
Well, and that's exactly my point. So, remembering this stuff, I don't want you to have to remember any of it. I really don't. So what I want you to do is be able to understand the mechanics of the steps of what I'm dealing with. And then if you can write down that little chart and write those 2 formulas down in the back of your book on that page, then you should be able to use those memory steps to plug in the actual steps on just about any voltage drop question. And just, you got to be careful of how you read the question, but you don't have to memorize any of it. You just got to kind of remember the steps. And if you can't remember the steps, you can always write yourself some bullet notes underneath on that same page back there. Step 1, if I'm looking for voltage drop, I'm going to use this circle, and then I'm, you know what I'm saying? That way you can, all you have to do is, and then all you got to do is remember where you put it in the book, and you're good, so that's
right.
And then you can save your gray matter for stuff that you can't do, something simple with, like, some of the motor stuff and things that you just got to know. All right. I've got, let's see here. I've got a couple more questions. I'm just going to go down the list here and just use these as examples, and I'm going to do a couple of them, and then we'll let you have some for homework. I may have to email them to you later, but I might be able to do them right now. All right, I've got number 5 here, which is determine a voltage drop on a conductor, where I've got 90 amps, 240 volts, single-phase load located 225 feet from a panel board and supplied with the size 3 copper conductors, K equals 12.9. So I'm looking for a single-phase load, 225 feet from this panel board. It's a single load, so it's probably going to be a branch circuit. Panel board meaning I'm looking at probably a breaker coming down, and then I've got my wires coming, which is number 3 AWG copper conductors. Now it's possibly that it could be that we're looking at a feeder calculation where this load might be a panel or something, but it doesn't really specify that. So we're looking at this as a 3% voltage drop as a branch circuit.
Okay. So
if I'm looking for what? Well, what are they asking me here? Well, I'm looking for the voltage drop here, actually. So in this case, I'm going to use the standard formula, which is 2 kids on the block. So it's 2 KID Where now, instead of the wire size, I already know what the wire size here is, don't I? Yep, number 3. So I'm looking for this value right here, which is the voltage drop. So I'm just going to write in the other value, and then I'm just going to leave that one off because that's what I'm looking for. This is my question mark. All right. So do I have everything I need? I've got my amperage load. I've got the fact that it's got the distance there. I've got the wire size there, and I've got a voltage value. So I've got everything I need in this equation to do this problem. So it's going to be 2 times copper, which is going to be the 12.9.
Okay.
And then I've got a load here. It's 90 amps. Now, a 90 amp load is one of those things that I'm suspicious anytime I have a 90 amp load that's, 225 feet. To me, that sounds like either a panel or a motor or something. But if they don't tell me in a case like this continuous duty, I'm not required to worry about it. So the vagueness of this question would lead me to just take the 90 amps and be done with it. Okay. And then 225 feet would be the last part of the top line. And I'm going to divide all of those by what the circular mills for a number 3 conductor are. And that is for number 3 on, again, back to table 8, third column there.
52,620.
Thanks. I just closed my book. 52,620, is it?
Yep, correct.
Not that I don't believe you, but I'm going to check anyway. 53,620. And it is 53,620. So I'm going to divide all that by 53,620.
52,620, right? Okay.
52, is that what you said?
Yeah, 52,620. Yep.
Okay. I could have sworn you said 53, and I looked up and could have sworn I read
sorry.
53.
Yeah, it's 52,620. Yeah, 52,60.
Okay.
Yeah.
All right. Thanks, sir. Let me just clean this up a little bit. All right, so that's going to be 52,620. All right, so the numbers at the top, we'll come over here, 25.8. Again, that first little step being this number here is going to be 25.8 every time it's copper, right? Single phase.
Gotcha.
So times 90 amps times the 225 feet, and that gives me on the top line there, oops, I think I did that wrong. I think I just punched the wrong button. 25.8 times 225 feet times the 90 amps. You do those in any order when you're multiplying them. 522,450 is what I got on the top.
90 times 225. Yep, 522. Yep.
All right, so that's my top line, and then I don't have to do anything on the bottom because it's just one number there. So divide that by 52,620.
Yep.
And I'm looking at 9.92873. And again, I'm just looking at 9.92. I'm assuming that they're going to drop that last digit.
Right.
Now, you look at the answer block here; they've rounded them all up to the next round number. So, but this is the actual amount of volts that I lost. If I put a meter out there, if it's instead of a 480 volt value, I'm looking at my meter giving me a value that's 471.08 volts there. So it's the physical amount of voltage loss that we occurred, and we're at percentage-wise. What is that? Oh, excuse me, it's 240 volts. Excuse me. Sorry, I was looking at the question right above, which is the 480 volt question. 9.92 volts. If I put a meter out there, it'd give me 231.08 is what I'd be looking at on a meter. Now, they didn't ask you for percentage, but just for grins and giggles. What does 9.92 volts represent percentage-wise? And there's an easy way to do it. So if I'm looking for volts, that's what this formula gives me, 9.92 volts, which in this case the answer block is given to me in volts, so that's all I have to do. I don't have to worry about it. But if they're asking me for what's the percentage, right? I'm still going to come up with this same number because that's what this formula is always going to give me, this real value, which is what I actually lose there, right? I'm just going to leave that in my calculator just like I've got right there. I'm going to hit the divide sign, and I'm just going to enter whatever the system voltage is, which is in this case 240 volts. So I'm dividing my answer by 240 volts, and when I hit equal, this is the percentage expressed in a decimal form, and if I move my decimal 2 places to the right, that's 4.13% is what that represents.
Yeah. Wow. Okay.
Sometimes
divide your
that's right.
Your voltage dropped by your 240 volts.
That's right. Just simply remember to take your answer and divide it by the branch circuit or the system voltage given to you in the question. And then that answer is going to be in decimal form. You just move it 2 places to the right, and that's your percentage. So, that's probably the toughest part, that they don't very seldom do you get that part of it out of any book or practice. It's just, I guess they kind of leave that to your own last final judgment. But for me, sometimes that was the hardest part. If they're asking me for percentage to convert that, it's real simple if you know how to do it. So as a note, I would probably put that down as a step, just to remind yourself the answer will always be in a real value, and to get the percentage, just simply divide your answer by the system voltage, and that'll give you what that represents percentage wise. Which we know that for a branch circuit, that's too much, right?
Yeah.
Now, I'll tell you that the truth is that this formula has got not very much of a real value to you as in the field, because to use this formula, you have to assume that every bit of your branch circuit load is at the very end of the branch circuit conductors. Which most of the time I've done a voltage drop. Maybe a single motor on one set of wires might be a good example of it. If you got one piece of equipment that's pretty big, kind of a far distance. But for parking lot lights, which is where the voltage drop really comes into play more often than not for us as electricians, if you try to use this formula for parking lot lights, where you've got a spread out amperage value that's not all at the end of the circuit, it's spread all over the whole entire branch. Boy, you'd run 3/0 or 1/0 to that first wire, that first couple of lights, and I mean it just doesn't work for you, because you don't have all of the load at the end of the branch circuit. So that distributed branch circuit amperage, like you'd have in parking lot lighting, you can't use this formula at all whatsoever. So the reality of it is, this is a formula that doesn't have a whole lot of really use, period, anyway. But
that's right.
But that's how you deal with it. And if you were dealing with it out in the field, you'd want to know what the percentage is, because that's kind of the whole point. So, if you did the math on it and you got that 9.92 volts, well, if you don't know how to convert it to percentage, you're just really not doing anything that's going to do you any good, because you just okay, well, I'm going to lose 9.92 volts. Well, you could have known that when you hooked it up.
Yeah, that's right.
So to do something with that, I'm going to have to then go back and say, okay, well, if this is 4.13%, now I can deal with this as a valuable number, because I know that 3% is my maximum. So I have to change one of these things up here has to change, or this one down here has to change. It's actually one of these three things. Either my amperage has to go down, which if I know what my load is, it probably won't go down, or I have to shorten my distance, or I have to make my wire size a little bit bigger. One of those three, and all three of those are the other three parts of the formula. So if I were to take this in the field and know this is too much, well, then I'd have to go back and say, okay, well, let's change the wire size, because we're cheap bastards and we don't want to shorten the length, or maybe you don't want to do whatever it might be. So you go back up to your formula there. And so instead of doing same formula, same exact steps, but instead of doing the voltage drop, you're going to fix that value there. Instead of being 9.92 volts, which is what we got out of this formula, we're going to fix this number at a maximum of 3% of 240 volts.
Yeah, wow.
Does that make sense?
Yeah.
A little bit? And so then you would turn around and do the same formula, but you would just divide it by the value that's in that little table that I was talking about. So at 240 volts, this 7.2 volts is the most I want to lose, not this 9.92. So I would just turn around and do the same top lines. That doesn't change. I'm just going to change this. Instead of using circular mills, I'm going to use this number instead, because the other part of this formula is the voltage drop or the wire size, one of those two. Well, if the wire size that I knew gave me too big of a voltage drop, well, then if I'm looking for the wire size, I would just simply take that top line, which this 2 kids doesn't change on the yellow circle. It's still going to be 522,450. So I just then turn around and take 522,450 and divide it by the maximum amount I want to lose on this branch circuit, which is this 7.2 at 240 volts.
Okay.
And I would know that I'd have to have a wire that's got at least a 72,562 circular mils. And so we changed that from a number 3 to a number 1, just like that. Bam, you're done.
Wow. Okay.
Now that being useful, you might actually use that. If you got a large load at the end of a set of branch circuit wires, that might actually be somewhat useful. But just like I said, don't try to use it for parking lot lights, because it's just going to give you some crazy numbers.
Yeah, that's right. Huh? All the way at the end. Okay. Huh.
So there you have it. That's just kind of a good review. Now, the maximum distance, that was the first one we did, and it's actually the tougher one out of the 4 to do, I think.
Okay.
Really, the amperage doesn't usually come up as a voltage drop calculation, because most of the time you know what the amperage is. It's almost like putting the cart before the horse, because what we deal with is loads usually as an electrician. So, this really, the truth is it's going to be, either one of these two variations where you're looking for either the VD or the circuit mills, or it'll be this one where you're looking for the distance. And so that's what I'd probably just kind of keep in my mind. But that's not too much. Yeah, you need to write those down, I think, and then the notes would be kind of the voltage. That little table that we had back there that I was talking about would be a good, handy thing.
Table there. Okay.
Yeah.
Is there any way you could email me those?
Sure.
2 or 3 things?
Actually, I'll try.
Table.
Let me see if I can just print a couple of these pages out, and I'll just send the whole stuff to you. I've got quite a bit of stuff on the chapter down here. That is the voltage drop stuff. Plus, we're going to do some of the Ohm's law stuff anyway. So I'm going to send this to you as a PDF. I've got it right here on another book.
Okay.
And let's see here. Probably
if we're going to go over it in class, I wouldn't worry too much. But
well, it doesn't hurt to have a little bit of a review ahead of time. That way, you don't have to you get a little bit of speed up time, so you're kind of on the same page when walking the door. It'll be almost like being able to go to the class twice, at least for these parts. So. All right.
That would be nice.
Let me get your email address real quick. I'm going to write it down on my page here. So I have it in front of me. Hold on for me 1 second. Let me get a pen. And then, so go ahead. What's your email?
It's wcnorth32@yahoo.com.
I've got Whiskey Charlie November Oscar Romeo Tango Hotel 32 at Yahoo.
You got it.
All right.
Yep.
Okay, I'm going to try to do it right now, but it'll take me about 20 minutes to kind of get the. I'm going to have to download my PDF reader and all that stuff. But I enjoyed it. I hope you got something out of this. And if you have any questions on anything we covered tonight, just kind of write them down, make some notes as you go along, and then I'll dig up some voltage drop examples to kind of throw in there too, so you'll have some of those to just kind of nail the finish nailing the lids in the coffin lid here. Nailing the nails in the lid of the coffin.
Yeah.
So tired, I can't even make my analogies.
Oh man, I know how it is.
All right, well, thank you.
Did the rain stop over there? Or?
Finally, yeah, I tell you, man, it just last week we were coming back from Houston from a class on Monday a week ago, and that was the worst rain I've ever seen. I think I told you about this already. I don't get intimidated or scared very much, but that stuff, man, I'll tell you, there was zero visibility in parts of it. I mean, literally, you could not see the road in front of you. You couldn't see lanes. You couldn't see nothing. Just solid sheet of water coming down. Then hail was coming down. I mean, there was tornado warnings on the radio. I mean, it was pretty nerve wracking. I got a little baby in the back seat. It's just it's a lot.
Yeah, it makes you wonder.
Yeah, a pregnant wife next to me. I tell you, just the responsibility and the amount of sheer. And man, I think we just walked through. We just passed by a couple of wrecks. That they'd shut off some of the roads, but I didn't want to stop because I couldn't see anybody coming from behind me either. So stopping in the middle, I didn't know where the shoulder was. I mean, I literally had to go on faith that I was even going and that I was staying in my lane and not in the oncoming traffic. I mean, it was scary.
Wow.
I'll tell you, it was man. Whew.
Wow, yeah, I wouldn't want to be there. That's right.
I was using my navigator, my GPS. I was using my GPS to make sure there wasn't any big curves in the road. That's literally the only way that we should probably survive. Yeah, that's how bad it was.
Holy hell, that makes me nervous.
But again, I appreciate you for letting me be late. I'm sorry about that, but
appreciate you talking to me on here. This will help quite a bit. Hopefully, I can practice it or figure it out.
Okay,
and then up to speed on it.
And then I'll get with Mel and tell her to set you up again. I don't know which class you come into, the one in Austin in a couple of weeks?
Yeah, Austin in a couple of weeks. Yep.
Okay.
I already got my flight and everything booked. So.
Okay. I know she's got me a pretty booked schedule this week, but before, like maybe on Monday or Tuesday of next week, if you got any time, we can do the second part.
Okay. Monday or Friday would be good. So.
Okay. And I've got a couple of people that I'm doing some other after the class stuff, and you're welcome to sit in and listen to any of it. It's one of those things that it won't be for you, but it never hurts. It seems like they have other people kind of pipe in with questions every once in a while, but they'd be primarily just whatever the other person needs. So I've got a 5 o'clock tomorrow, and then a 5:30, which is a master's for Texas on Wednesday. And then I don't think we have anything scheduled for Thursday evening. And then Friday I've got blocked off. Saturday I've got blocked off, and Sunday's family time. So it'd be Monday, or if you wanted to, like I said, listen into the Wednesday night deal or Tuesday night, either way. But just text her or whatever, and she'll let you know.
All right. Okay. Perfect.
All right, sir. Have a great evening, and be careful out there.
All right. Okay. Thank you, Mitchell. Appreciate your time.
No problem.
Okay.
Bye-bye.
Bye now.
And that is a wrap for